And we are now live. And so we'll see in just a little bit. Let me give it about 20 or 30 seconds to see if anybody pops in. Okay, so we welcome everybody, whoever's watching. We're going to continue with our Unit 4 discussion and lecture that we didn't quite get through on Wednesday. And so if you are watching this as a live viewer, but not an active participant, you can use, if you find at the top of your screen, you should be able to find a little grid, just sort of a 3x3 grid. If you click that, that should allow you to open up a Q&A panel where you can actually type in questions if and when you have them. For anybody who's participating as an active participant, right now we only have one, then you don't have access to that panel, I don't believe, but you can just verbally ask the questions. Okay, so let's get started. I'm going to share my screen now. And so what you'll see is just the PowerPoint presentation. Actually, it's a PDF, but let's see, I guess I want that one. Okay. So can you see that, Adam?
Yeah, I can.
Okay, does it look clear and everything?
Yeah.
Okay. Okay, so what I'm going to do is just so I'm just going to start off by reminding folks where we kind of left off before we move on. So we had just finished this discussion about centripetal acceleration. We did a problem, a student sitting in a desk in Salt Lake City and calculating the centripetal force, the net force on that student as the Earth rotated on its axis. And I just want to remind people that there's a few things we have to keep in mind here when we talk about centripetal acceleration and force. There is, if an object is moving in a circle, then there will always be a component of the acceleration and the force, which is directed towards the center of the circle or the center of the curve, which we call centripetal. But that doesn't mean that there is a new force, which is, every situation basically will give you a different actual force that is responsible for that centripetal acceleration. And so it could be tension, it could be friction, it could be gravity, lots of different things. But if it's directed towards the center, we generically call that centripetal force, basically because it causes the centripetal acceleration. If an object which is going around in a circle is also changing its speed, it's either speeding up or slowing down, then it could also have a tangential component of acceleration. If it's speeding up, that tangential component would be directed forward. If it's slowing down, it would be directed backwards. And so you can have the total acceleration may not be purely centripetal. It could be, it's a vector, so it could have a centripetal component and a tangential component. So we just have to keep that in mind. Okay, and then, so we had basically gone from the idea of circular mechanics, so kinematics for uniform circular motion, where you have an acceleration directed inward and velocity in the direction of motion, so it's tangential. And basically, when we think about dynamics, we think about forces and momentum instead of acceleration and velocity, and they're related simply by the mass. Okay, and so we multiply the acceleration by the mass, we get the force that's required to keep the object moving in a circle with that acceleration, and we multiply the velocity by the mass, and we get the momentum. And again, these are vectors, so the force points in the direction of the acceleration, and the momentum points in the direction of the velocity. Okay, so before we move on, I just want to remind, there was a particular question on the pre-lecture, Unit 4 pre-lecture, which seemed to be challenging for folks. So I wanted to kind of hit that again in the context of this little question that we did in class on Wednesday. If we have two velocity vectors that are, what we did was we showed that if we have two velocity vectors pointing in these different directions, so we have v1, which is sort of the initial velocity, v2, which is the final velocity, then the difference, the change in velocity, delta v, is v2 minus v1, and it's basically directed nearly to the left with and a little bit downward. These two velocity vectors have the same length, and so that leads to a slightly downward component of the velocity as well, but mostly to the left. And so we also then talked about that in the context of centripetal acceleration and how the acceleration, the change in velocity, and the net force are all directed inward towards the center of motion, center of the circle. Okay, and so this was the question that appeared on your pre-lecture, and I wanted to make sure that we were clear on this because there was quite a spread in answers on your pre-lecture. So here's the question. We have a force F acts on a mass m during the time period from t equals 0 to t equals 1 second. The force, as you can see, is directed to the right. It's applied to this mass. The mass moves with velocity v1 shown at time t equals 1 second. So at the end of this period, so at t equals 1 second, the velocity is in this direction, v1. And the question is, what's the velocity at the beginning at t equals 0 when this force is, just as this force is starting to be applied? Okay, and so that's what the question here, and here were the choices that you had on your pre-lecture. And as I said, there was quite a spread in answers. So just to give you an example of the kind of data which I can get from smart physics, here are the distribution of your answers. The first answer that you chose as a class, and you can see there were 139 of you that actually voted on this pre-lecture question. And so that's the distribution of answers. And so the way that we want to look at this is that if we have a force that's directed to the right, then by Newton's second law, which is F equals ma, here I've written A in a very particular form. I've basically just called it the change in velocity over the change in time. And if it's a constant acceleration or delta t is small enough, this is perfectly legitimate. And so what we see is that the force and the change in velocity vector, as we've discussed before, are in the same direction. So that means, since we know the force is to the right, that the change in velocity vector has to be to the right. And so if we started off, I mean, if at t equals 1 second, we have a velocity which is perfectly vertical upward, then in order to have this change in velocity resulting in this final velocity, our initial velocity at time t equals 0 must be pointed up and to the left. So that when you add v0 to delta v, you get the second or the final velocity. So v0 plus delta v is equal to v1, and that's so that would be the correct answer. Then would be D. And so if we back up a second, we see that only 25% of you or so got that correct on the first time, and so I wanted to go over that. So, are there any questions about this before we move on? Sort of our next topic. Okay. Again, if you are viewing this using Google Plus, or you're viewing this with, or if you're viewing this with a on YouTube, then well, if you're viewing it on Google Plus, then you should be able to activate a Q&A panel where you'll be able to type questions, and then if I see those questions pop up, I can see those pop up in my panel, then I will I'll answer them. So far I haven't gotten any, and so please take advantage of that. Okay, let's move on then. So the thing I really wanted to talk about that we didn't get a chance to talk about on Wednesday was this idea of, sometimes maybe you've heard of Newton's second law just expressed F equals ma, but we have to keep in mind that F, that force, is actually the net force on the object. If there's only one force acting on the object, then of course F equals ma works just fine. But in general, we have to add up all the forces, so we have to do a sum of all the forces acting on the object. We call that sum of forces, that vector sum of forces, we call that the net force. And then if we divide that by the mass, then we get the acceleration. So here's sort of a graphical representation of that situation. And again, we covered this, we basically just got to this at the end of class. So we have 4 forces acting on this object in different directions and different magnitudes. And if you do a vector sum, if you basically add up all these vectors tip to tail, one of the things you'll find is that F2 and F3 are equal magnitude but opposite direction, so they're going to cancel. And F1 and F4 are in opposite directions, but since F1's larger, the net force will be to the right. So the residual force will be to the right, and that means that the acceleration of this mass will be to the right as well, as indicated. Okay, and so again, just in general, if you have a bigger mass, then the acceleration, you need more force, more net force to cause a particular acceleration. Okay, so let's kind of work through this using an example problem. And because we only have one person tuned in live, then we probably won't be able to do any sort of voting like I had planned to do in class, but we'll work through this nonetheless. So what we have is a situation, and this was on a quiz or an exam some weeks ago, a few years ago. We have 2 blocks, block A and block B. One's on the left, one's on the, block A is on the left, block B is on the right. These are in contact with each other, and they're sliding together on a frictionless horizontal surface. So you have, you're pushing one of the blocks, you're pushing on block A, and you're pushing it to the right, and that causes both blocks to accelerate to the right with an acceleration that we'll just generically label small a. So block B also has 5 times the mass of block A, so that's an additional bit of information that we can use to solve the problem. So the question is, what is the net force on block A? Okay, that's one of many questions that could be asked about this scenario. Okay, and so as usual, what we want to start off with is a problem, so we want to kind of use our general framework. So we want to understand the problem. And so one of the questions we might want to ask ourselves after reading the problem a couple times and making sure that we understand actually what's written, then one of the questions that we might want to ask ourselves is, why do the blocks move together? Why are they, you're pushing on one, why are they moving together? And probably most of you will be able to kind of intuitively understand, because if you push on one of them, then, and the other one is in the way, they can't pass through each other. Okay, and the implication of that is that the acceleration of both blocks is the same. And so whatever acceleration block A has, that's the same acceleration as block B. And you could say that if you had one block of mass A plus B, then that would be the acceleration of that compound block as well. Okay, another question you might want to ask is, what is the direction of the net force on block A? Okay, and that one, if we understand Newton's second law, we know that net forces and accelerations have to be in the same direction. And so since both of the blocks are accelerating to the right, it must be that block A, that the net force on block B is also to the right by Newton's second law, as I've written. Okay, so any questions or anything that anybody would want to add to that? Looks like we've got 2 folks now. So any questions from you guys? No, we're good? Okay, so then we would want to describe the physics. So that would be the second step to, in our framework of solving the problem. So one of the key things to do when you're sort of describing the physics, obviously, is just sort of write down a useful diagram. So here I've tried to capture what's written up here in a diagram. Here's block A, here's block B. It says that block A is on the left and block B is on the right. It also says block B is more massive than block A. So just to remind us of that, I've made it bigger. might not be bigger, might just be made out of more dense stuff, but that's just a graphical way of representing that. We also know that we're pushing block A to the right, and so we have our hand would be pushing on block A, and I've represented that force, FH, with an arrow there heading to the right. We also have an acceleration to the right, and so we can draw that in. And finally, we might want to draw, it's usually a good idea to draw some sort of coordinate system. In this particular case, it's pretty obvious that this is a one-dimensional problem. We don't have any motion or accelerations along the y direction. And so it's, we really only care about the x direction, but just for completeness, I've drawn a two-dimensional coordinate system here. And so we can, taking Newton's second law, A equals F net over M, then we can divide, we want to always keep in mind that the acceleration and the net force, these are vectors. And so they have, in this case, we're going to neglect a z. No, there's no interesting motion along the third dimension z. So we remember that the vectors are just, this notation is just shorthand for remembering that we have two components, or three components in general, but two components we're going to care about here, ax and ay. And so this equation up here can be written, if we think about the components, as it is down here. And then, so since there's no acceleration again in the y direction, we only need to consider horizontal forces. So in the end, we're only going to care about ax and f net x. And I'm just going to call that a and f net, since we've only got one direction to worry about. Okay, so here's a second step. Yep, you got a question? Somebody have a question? Okay. So let me see. I'm going to mute that. Okay. So we have a, here's a, in terms of, in the process of describing the physics, then we can consider, at least at some stage, we can consider the two blocks as being composed of a single block, being basically one block. We'll call that block A plus B. Obviously, the mass of that composite block is the mass of A plus the mass of B. Okay, so basically we can consider, if we're pushing on the blocks to the right, we can basically consider that they're stuck together because they're moving together, they're accelerating together. Okay, and so your hand, just like in the previous, just like in the example that we, okay, hold on a second, I have a question over here. I have a question that says, can you really say that there is no, so let me just select that question just a second. Can you really say that there is no force in the x direction because what about gravity? Does that not count? Okay, so there is no force in the y direction. I mean, there is a force in the y direction. Gravity is, you're absolutely correct. But gravity acts downward, and that, as we'll learn on Monday, that is balanced by an upward force from the actual surface. So the downward gravitational force and the upward, what we'll call normal force or support force, are exactly the same magnitude but opposite in direction, and they act on each of the blocks in that way. They can't, so they basically cancel out. And so the net force in the y direction will be 0, and so there'll be no acceleration in the y direction. And so that's why all the motion is happening in the x direction. Thank you very much for that question. Okay, let's move on here. Okay, so again, if we think of the blocks as the two blocks as a composite, then we have a situation like this. And so from this, and from if we think about it like this, then we can actually easily find the magnitude of the force FH, the force from your hand, okay, the pushing force. Okay, and so if we were in class, I would basically have you vote on this. Since there are only 3 of you tuned in, it doesn't make any sense to vote. And so we'll just work through this, right? So the answer is ma plus mb times a, where a, again, is the acceleration. How does that work? Well, again, we start from Newton's second law. There are no other horizontal forces acting on the composite block. There's no friction, and there's only one force pushing this composite block to the right, FH. And so the net force on the composite block is the force from your hand, FH. And so the magnitude of that of FH is just m, the total mass, which is ma plus mb, times the acceleration a. And it's important to understand that as the problem is framed, we should take a as essentially a given quantity, and we should also take the force from the hand as essentially a given quantity, because what we're asked to find is the net force on block A. If we go back, we're asked to find the net force on block A, which that's the unknown here, and so we would have to assume that A and FH are given. In the problem, we might be given numbers for those things. Any questions about that from the peanut gallery here? No? No? Okay. All right. So we're still describing the physics here. So you'll notice that when we do these problems according to our framework, when we do these problems together in class, that we almost always, the longest part of the problem solving framework is describing the physics and planning your solution. And that's where the hard part is. And so that's why that usually takes the longest time. Okay, so back to this problem. So now we know the magnitude of the horizontal force, the force from the hand, sorry. It's equal to ma plus mb times the acceleration a. And so even if we now, again, think about these two blocks as separate, you've already found the magnitude for the force from the pushing force, the force from the hand. Okay, so given that, another question that we could ask to understand the physics here is, I already said that the only horizontal force acting on the composite block is the force from your hand, and FH, and so is that equal to the net force on block A? That's what you're actually being asked to find in this problem. We found the force from the hand. Is the force from the hand, FH, equal to the net force on block A? Okay, so the question is this equality correct? Okay, and so we can write down the left and right side of this equation. We know that the force from the hand, we just solved it. It's ma plus mb times the acceleration a. And we know that on the right-hand side, sorry, the net force on block A is, by Newton's second law, must be equal to the mass of block A times the acceleration of block A. And because the composite block, both blocks are accelerating together, A in both sides here is the same. And so we can cancel it out, and we see that this equality cannot be true. We can't have ma plus mb equal to ma unless one of them were 0. Okay, and so that can't be true. And so what this means is, if we think through the physics here, is that there must be other horizontal forces on block A besides the force from your hand, FH. So this is a really sometimes subtle but important thing to understand. When we consider the two blocks as a composite block, then there's only one horizontal force, and it's FH. But when we think about the blocks as separate blocks, block A, block B, what we're finding is that there's at least one additional force acting on block A besides the force from the hand, FH. Because if there weren't, then this equality would be true, and this equation here would be correct, and we see that it can't be. Any questions about that? It's kind of an important step. Okay, so let's move on then. And so what's going on here, right, is that we have Newton's third law. We have, whenever you have two objects that are interacting, that is exerting forces on each other, these forces come in pairs. So if you have a person here pushing on the wall with some force, which we'll designate as F man wall, force from the man on the wall, then the wall pushes back with that same force, the same magnitude force, but in the opposite direction on the man's hands. Okay, and so you have these equal and opposite pairs of forces that are, and we call those Newton's third law pairs, and we can capture the essence of Newton's third law with this up here. The force of object A on object B is equal to negative the force of object B on object A. Okay, so it's easy to get confused with the notation here, A, B, B, A, and it doesn't really matter really which one is the one doing work, which is the one pushing on the other, as long as you're consistent, okay? Here, the notation that smart physics uses says force of the man on the wall. So A is the thing pushing, B is the thing being pushed on, okay? But the really critical thing here is that we have to realize that although these are equal and opposite forces, those two forces are actually acting on different objects. So the man pushes on the wall, and so if you ask a question about what's going on with the wall, then you consider that force. And you would not consider the force of the wall acting on the man, because that wall, the force that the wall acts on the man does not affect the motion of the wall. And similarly, if you ask a question about what's happening with the man's motion, you only consider the forces acting on it, not the forces acting by it. Okay? And on Monday, I'll do our little rocket demo, and maybe somebody of you guys can ride the rocket. Okay, so any questions about that? What we just, this Newton's third law. Okay, so let's do, well, we can't really do this, but in class, let's think through this. So imagine that we have two people that are running towards each other, and they're going to collide. And so we have a small guy and a large football player, and they're moving at the same speed, okay? So these arrows are meant to represent their velocity vectors, and so they're the same length. And they're going in opposite directions, so they're going to collide head on. And which person experiences a larger force during the collision? Okay, so the choices are the small person, the small guy, the football player, or do they experience the same force? Okay. And Newton's third law basically leaves no ambiguity here, right? If two objects are pushing on each other, if they're exerting forces on each other, if they're interacting with each other, they push on each other with exactly the same force. Okay, so they experience the same force, which is maybe a little bit counterintuitive, because we know if this situation were to happen, the big guy just kind of keeps running. He hardly gets slowed down at all, and the little guy just gets crushed. Okay, and so that kind of goes to this question. Same situation, which person experiences a larger acceleration during the collision? Okay, and so here, even though they experience the same force, the small guy experiences the larger acceleration because the acceleration is equal to the force divided by the mass. And the way this problem is phrased, it's clear that the small guy has less mass and they experience the same force. And so the acceleration of the small guy is the magnitude of the acceleration anyway is larger. So the small guy stops, might even bounce backwards. So their velocity, so the small guy's velocity is changing from going to the right, perhaps to bouncing off and going back to the left. That's a large change in velocity, which means a large acceleration. The big guy, he experiences the same force during the collision, but since he has a lot more mass, he just his velocity hardly changes at all. He just sort of plows right through. Okay, and then finally, you could one other way that you could think about this is that you now have the small guy is the only one that's moving. The big guy is standing still. They collide, and even though that seems like a different situation, and the resulting motion for the two guys may be different than in the previous example, again, they experience the same force. Okay, and that Newton's second, again, Newton's third law does not leave any ambiguity about that. So any questions about that? And show Sita, I'm going to unmute you. Okay. All right. Okay, so we're still in the middle of this problem, so we're step 3 now. We've kind of understood the physics, now we can plan our solution. So again, the question is, given the scenario, what is the net force on block A? Okay, so the force from the hand, FH, must be, again, we should consider this a given variable because the problem is asking about a different force. And so in order for us to solve this problem, we would either have to consider that a known variable, or the problem would provide a number for that. And so what we need is an expression for the net force in terms of the force pushing from the hand. We can probably understand that if the FH, if the force from the hand gets bigger or smaller, if it changes, then the net force on block A must also change. And so it's reasonable to think about finding an expression for the net force in terms of how hard you're pushing on block A. Okay, and so we've already expressed the acceleration of both blocks, so including block A, in terms of the force from the hand, FH, and the two masses. So we've already did that. We've already done that, and I've written it again there. And we also have a relationship between the two masses. So we have, the problem tells us the mass of block B is 5 times the mass of block A. So I've just basically converted that sentence into an equation down here. Okay, so given this relationship and this relationship, then we can now, we're poised that we have everything we need to find the net force on block A in terms of the force from the hand, FH. Okay, and so we would then just execute the solution. So we start with this equation that we already found, this expression that relates the force FH to the masses and the acceleration. Okay, and we know that block A also accelerates with acceleration A. And so the net force on block A, this is just Newton's second law, F net over MA is equal to the acceleration of block A. Okay, and so these two things are equal to each other. And so we can solve that equation for the net force on block A just by multiplying this equation here by MA. And so this is the expression that we get. Okay, and we see that this would complete the problem. Okay, if this was the end. So for example, if we knew the masses of MA and MB and we knew the force from the hand, then we'd be able to get an actual number for the net force on block A. We are told that block A and block B are related in terms of their masses. So block B is 5 times the mass of block A. So we can actually substitute for MB here. We can substitute 5 MA. So we can put everything in terms of MA, and then those MAs cancel, and you get 1 over 6. And so what we see is that the net force here on block A is 1/6 of the force from the hand. Okay, any questions about that? We're all good there? Okay, so then you would, we also want to just kind of ask ourselves, does this make sense? So one of the ways that we can do this, so we've just solved for the net force on block A, and so we found that that's 1/6 the force from the hand. If we did the same procedure for block B, basically Newton's second law says that the net force on block B must be equal to its mass, MB, times the acceleration A. Okay, and that will allow us to really quickly to find the net force on block B. It's equal to this FH divided by MA plus MB. This part of this equation, right, which comes from up here, is just the acceleration, and you multiply that by the mass of block B, and that gives you the net force on block B. And if we, again, substitute MB is equal to MA divided 5MA, then we find that the net force on block B is 5/6 times the force that you're pushing with. And so this now starts to make sense. If you add up these two forces, the net force on block A and the net force on block B, you get the force from the hand, FH, 1/6 plus 5/6. And so that basically just says that the hand is pushing both blocks. Well, it's pushing block A, causing both blocks to move. Only 1/6 of that force is actually what is moving block A or accelerating block A, and 5/6 of that force is accelerating block B. Okay, and so what this means, right, is that force block B is in fact pushing to the left on block A. Okay, it's pushing to the left, and it's pushing with a force of 5/6 FH. So the same, the net force on block B, because it's the last one, there's nothing to its right. The only horizontal force on block B is actually the force from block A pushing on it, and by Newton's third law, that means that the force that the block B pushes on block A with that same magnitude force, but in the opposite direction. So minus 5/6 FH. Okay, so a perfectly legitimate problem could also have been, how hard does block A push on block B? So that would be a perfectly legitimate question to ask relative to this scenario. And then you could work through it in a very similar way to find that the force that block A pushes on block B is equal to 5/6 times 5/6 the force of the hand. Okay, so that is the end of the lesson. Are there any questions before we stop our broadcast? No? Any questions from the viewers, the non-live, the live viewers? Any questions that you want to type? No? Okay then, folks, I will see you on Monday. Have a great weekend. Don't forget that your homework is due tomorrow at midnight, just Unit 4. Okay? Have a good one.